So, do you think that for the discovery of the entire makeup of the universe and the most adorable yawn ever captured on camera, that Cecilia Payne, my golden doodle, should win the
Mm.
Physics Nobel Prize?
On the one hand, that's, an incredibly amazing discovery. And also on that one hand, that is the cutest dog I've ever seen, and that dog is incredibly adorable. On the other hand,
Just give up.
Yeah.
Hello and welcome to Bad Astra. Today we will be chatting with Dr. James Lasker. Dr. Lasker is a postdoctoral researcher at Southern Methodist University working on the Dark Energy Spectroscopic Instrument, or DESI. Dr. Lasker earned his PhD from the University of Chicago, defending his thesis on the measurement of the Type 1a supernovae rate for the Dark Energy Survey, or DES. He also worked on absolute photometric calibration of DES and on corrections of supernova photometry due to atmospheric variations in the effective survey transmission function. He's part of SMU's DESI research team with responsibilities ranging from operations to analysis of baryon acoustic oscillations, as exhibited in the large-scale structures of galaxy clustering. Most importantly, Dr. Lasker captained the UChicago Astronomy Department's intramural softball team, Little Mingo, to multiple championship wins. James, could you tell us a little bit about what dark energy is and why we should care?
Dark energy is one of the fundamental components of the universe, along with matter, which is, just things you can see around you, like this computer or you. That makes up about 4% of the. Yes, you matter.
Aww.
Everyone matters. So that's about 4% of the universe. Dark matter, which is similar to ordinary matter in that it has mass, but doesn't. It's not visible, hence dark. It makes up a lot more of the universe than ordinary matter, is about 25, 26%. And the remainder of the mass of the universe is what we call dark energy. So it's about 70% of the universe's total mass energy. There's about 15 times as much dark energy as there is ordinary matter, and over 3 times as much as there is dark matter. So it is pretty easily the most significant component of the universe. But we don't know too much about it in general. What we do know is that, unlike ordinary matter, where if you were to take relevant, a thing of hand sanitizer, if you squeeze it, the air pressure on the inside, it builds up and it pushes back at you with its pressure. Dark energy, if you were to somehow have a ball of it, if you were to squeeze it, it would actually pull back in further. If you were to pull on it, it would then pull even further. So unlike ordinary matter that we know of, it sort of behaves exactly the opposite.
Dark matter is not at all the same thing as antimatter.
No, antimatter is mostly the same as the ordinary matter that we see. It does interact with light, but it's sort of everything is the opposite in antimatter as it is in regular matter. So the spin is opposite, the charge is opposite. And if you have a ball of antimatter and a ball of matter and you just bang them together, they instantly annihilate and they turn into a big thing of pure energy. Dark matter behaves the same as matter in that it attracts things that have mass. The same antimatter also behaves in that way. If it has mass, and it will attract both matter and antimatter with mass. Dark energy it behaves the opposite of matter in terms of it's like pressure. The pressure that it exerts on the universe. Dark energy, the easiest way to understand it, I guess, is to think of it like wind, that we can't see it, but we can see what it does. So dark energy, while we can't observe it directly, we can observe what it does to the expansion of the universe. And what it does is that, unlike normal matter, which pulls in on the universe, has a gravitational pull and tends to slow down the expansion of the universe, dark energy, it pushes on the universe and it makes it accelerate, it expand faster or accelerate. And that's actually how we discovered it, by trying to measure the expansion history of the universe using type 1a supernovae. And what the measurement actually was, that based on a universe that didn't have any dark energy and it just had ordinary matter and dark matter, the supernovae that were observed, they appeared to be about 20 to 30% fainter than they would have if the universe only had dark matter and ordinary matter. And that was interpreted as the expansion of the universe being faster more recently due to the action of dark energy.
And just to clarify, when you say type 1a supernovae, you're talking about how they can be used as standard candles,
Yes.
so we know exactly how bright they are, not anything specifically special about supernovae. Dark energy doesn't specifically affect type 1a supernovae. It's just that with type 1a supernovae, because they always act in the same way, we know how bright they're supposed to be. So if they're a different brightness, we can assume they are further away than we expected, or closer.
More or less, that's how it works. Yeah, there's no preferential activity of dark energy on any specific objects. Type 1a supernovae are the formation of them is still a subject of a lot of interest. It was related to my thesis because supernova rates are one of the ways that we can infer the formation mechanism of type 1a supernovae. But regardless of how they're formed, there are some well-known, well-measured relationships between the light curve decline rate, so how quickly they go from their peak brightness and fade away, as well as their color, whether they appear more blue or red. And those, when you measure that, the duration and the color of the light curve, you can measure how bright the supernova should be in an absolute sense.
So that's how we know dark energy exists, is that the universe
Yes.
is expanding faster than it should be.
Yes.
So what is dark energy? Obviously, that's a loaded question because your whole thing is trying to figure it out. But what has been ruled out?
One of the earlier explanations is the amusingly named Hubble bubble, named after Edwin Hubble, University of Chicago basketball player and also astronomer, and namesake of a space telescope that you might have heard of. He made the first measurement that the universe was expanding. As such, the rate of expansion of the universe is named after him, the Hubble constant. And this Hubble bubble hypothesis is that we live in a void in the universe, a void being a place where there's less matter than there is normally, which would lead us to measure an anomalously high value for that Hubble constant locally. And that was disproven.
That's an interesting theory, that we live in a Hubble bubble. We are just so unique.
Yeah.
That the laws of physics that we have determined work for the whole universe, just not for our little corner of it.
Yeah, so that goes against every principle of modern cosmology. It's called like the cosmological principle is that there is no unique position in the universe. There's no preferred location or direction. And that hypothesis sort of went completely against that. And it was measured in like the early 2000s that it is highly unlikely that there is a local void that could cause this, based on all of our measurements of, local galaxy clustering and some local type 1a supernovae. The current favorite explanation, I should say, it's the cosmological constant, that there's some sort of vacuum energy density that as the universe expands, there's just a constant energy density present in all the new space that results from the expansion. And that was originally accidentally proposed by Einstein in like 1919 with general relativity.
Yeah.
He sort of said that it was his greatest blunder, that he proposed that, and he threw it out around the time that, more or less right when he developed it, because around that same time, Edwin Hubble discovered that the universe was expanding. He'd originally added it so that the universe could remain static, which was the accepted theory of the time. And 90 years later, when the supernovae were measured to find that the universe's expansion was accelerating, the cosmological constant was a very convenient mathematical form to put in to explain the acceleration.
It always comes back to Einstein.
Pretty much. We've been testing general relativity for over 100 years now, and it's passed every test that we've completed.
Well, actually, there was a guy who commented on one of my videos linking me to his Google site. He has disproven really all of Einstein's, specifically general relativity. This wasn't even on my general relativity video that this comment was made.
I wish I had this book with me. I think I left it at home. If someone left a book in the lobby of not the lobby, the Astra Lounge in ERC, and the title was like, "Why Einstein Was a Complete Fool," and the cover was just this spiral of, I think it was the elements and atomic numbers, and I read a couple pages, and it was magical. Like, it was magical in the sense that, like, the guy must have been on some amazing drugs.
Yeah, for all of you out there who have heard anyone say that Einstein was a fool, or who think that you yourself have disproven Einstein, I'm very sorry, but virtually all astrophysicists disagree with you, with the exception of maybe a few quantum theorists.
Well, so this isn't to say that, general relativity has to be the theory, but the problem with most theories that are trying to explain, the universe that aren't general relativity is that in tons of different applications, it has to look exactly like general relativity. Like, it has to produce gravitational waves. It has to produce gravitational time dilation. It's all of the effects that we've tested from it. They conform to our measurement precision in what general relativity predicts. So it's not that there can't be extensions to general relativity, that there can't be things that are other theories of gravity at different scales.
I mean, but if you look at it a certain way, general relativity is almost an extension of Newton's laws of gravity.
It reduces to Newton's laws of gravity when you go to small masses and larger forces.
Yeah.
Am I doing that sign right? It's definitely smaller masses, like it.
Yeah.
But
it's smaller masses and lower speeds. Basically, Newton's theory of gravity is actually just a special case of general relativity. The way we think about it is different, but Newton wasn't wrong. He just had a very limited scope with which to work. Then we developed all these instruments that could see all these other cases, and we found that it wasn't Newton's laws of gravity wasn't a universal application, and Einstein's theory of general relativity works in almost all of the cases we can currently find, except for quantum mechanics, which is grand unified theory stuff, and that'll likely be an extension upon the work of Einstein.
Yeah, well, just like general relativity works on the larger scales, quantum mechanics works on the smaller scales, and there is something that's going to connect that, and whoever discovers that is going to have a very nice Nobel Prize in their future.
And all of the people who think they've discovered it can comment on this YouTube video.
Yes, please leave your comments. They will be nicely ignored.
I will enjoy reading them. They will help engagement. I'll have a nice glass of wine. If you want to make some joke comments, I will also love and read them.
Yeah.
So to summarize what James was saying about the current leading theory of dark energy is just that the dark energy is basically space itself. We learned from general relativity that space can be warped. Space isn't just a blank stage. So dark energy, the current leading theory, is that space has an inherent energy and inherent properties of its own.
I wanted to mention one of the more amusing, I guess, stories from cosmology, which is that once people thought that, oh, this cosmological constant, it could be a vacuum energy. Let's look at quantum field theory and let's see what happens when we try and, write out all the equations and figure out how much energy there should be. Vacuum energy there should be according to quantum field theory. So they did it, and they determined that in order to agree with what was measured by cosmologists, by astronomers, they were off by 120 orders of magnitude. The difference between the entire mass of the universe and the mass of a proton is 80 orders of magnitude. So it is 1,000 trillion times bigger than that. So they were very wrong, but there's a lot of potential for interesting physics that can explain why that vacuum energy that is predicted doesn't necessarily get translated into the dark energy effects that we observe.
So now that we've gotten a baseline on dark energy, what we think it is, what we know we've ruled out, if our theories about how physics work are correct for the most part, dark energy has to exist. We have some ideas, we're not sure. How does your research tie into it? What do you do specifically?
So right now I'm working on an experiment that you mentioned, the Dark Energy Spectroscopic Instrument, or DESI. It's run out of a telescope near Tucson, Arizona, at Kitt Peak Observatory, which you should all visit, once it's safe to travel, because it's a beautiful place. And DESI is a technological marvel. It's the next stage of the natural progression from Isaac Newton pointing a prism at the sun and watching it form a rainbow, to taking a prism, or a set of prisms really, and pointing it at 5,000 different galaxies at a time, and getting the spectrum of light, divided up into wavelengths of all those different galaxies at the same time. And because we have this robotic network of fibers that are beyond this prism getting these wavelengths, we can measure the redshift of all of these galaxies. Redshift being the amount that the spectrum of a galaxy is shifted towards the red because it's moving away from us because of the expansion of the universe. For millions, hundreds of millions of galaxies over the entire sky. And we use that to create a three-dimensional map of the universe. And three-dimensional meaning 2D, we know where everything is on the sky. Getting those positions is relatively easy, although the observing campaign needed to actually image all of these galaxies is incredibly impressive. The main goal of DESI is to then get these redshifts to take that two-dimensional thing mapped all over the surface of the sky, and then say, well, these galaxies are out here, then these further redshifted ones are further away, and get this 3D map.
So people watching this might be familiar with the Doppler effect. Basically, something coming toward you, if it's emitting a sound, will sound higher pitched than when something going away from you. So the classic example is as an ambulance passes by, the siren sounds higher pitched as it's approaching and lower pitched as it's leaving. That's because as it's approaching, the waves get compressed, and as it's leaving, the waves get stretched on their way to see you. In space, that also works just on a much larger scale. The further away galaxies are from us, the faster they are moving away from us in a very measurable way. Through spectroscopy, we can identify hydrogen lines. There are 4 lines. We can pretty much pick out where they are. The most common element in the universe is hydrogen. And if you can find what the 4 hydrogen lines are, you can see where they're showing up. So if a line should be showing up in the visible red and it's showing up all the way in the infrared, you know that it's redshifted by that wavelength. So the amount that it's redshifted by, that you're reading, can be used to figure out how far away it is. It's a decently simple calculation. Well, not simple, and obviously finding where those hydrogen lines are, because they're of course in the wrong place, that's how this works, is difficult. So these are all very complicated things that are done by computers for countless galaxies. Like, do you know how many galaxies DESI is doing this for just in a day?
In a day. So we have we spend like, what, 20 minutes per observation. So let's say 3 to an hour, 10 hours, 12 hours probably an average night. Duh. So let's see, 36 observations by 5,000. Somewhere in the neighborhood of like 150 to 180,000 a night on a good night. Those who have been observing, whether amateur observing or at like a professional observatory, will know that weather does not always agree. But on average, it's about 150,000 targets per night. And we usually need about 3 targets, between 2 and 3 targets of a certain galaxy, of an average galaxy, to get a good redshift.
Okay, so you can get a good measurement of how far a galaxy is away. After 3, you do 150 a night. So basically, every day we're learning how far away an average of 50,000 galaxies are on a good night with good weather.
Yes. While redshift is a good proxy for how far away a galaxy is in a relative sense, we're also interested in how far away they are in an absolute sense, which requires some sort of distance calibration. Now, the type 1a supernovae that I mentioned earlier, those get calibrated sort of from the local universe up in what's called the cosmic distance ladder. We start with parallax. To envision parallax, just sort of hold your finger out, close one eye and look at it, and then close the other eye. And you'll see, as you do that, the position of your finger, it moves apparently relative to the background. And we do that for stars and in the Milky Way. And we then have stars we take those stars at known distances and we can measure their brightness. We find standard candles similar to type 1a supernovae, but in that we know how bright they are based on observations of their luminosity and how it varies in this case, the Cepheid variables. And for those stars, we know that how often they pulsate to a peak and a trough, how bright they are. The longer it takes, the brighter the star. And that's one rung of the ladder. So we go from Earth via parallax to Cepheids in the galaxy, to Cepheids in other galaxies. And then we can use that distance to calibrate the distance to type 1a supernovae. And using those supernovae, which are incredibly bright, often as bright as the galaxies in which they appear, we can measure out into the very high redshift universe. But with DESI, we're actually going the other direction. we're going back from the furthest observable history of the universe, the cosmic microwave background radiation, the baby picture of the universe, the afterglow of the Big Bang. The cosmic microwave background is radiation that's been traveling through the universe since...
Last scattering was 380,000 years after the Big Bang.
Yes. And it's been traveling since then. And I don't think it's possible anymore because of the transition to digital TV. But in the olden days, with the big big funny rabbit ears, you could, if you tuned to a channel that was just static, there was just nothing on the channel, you would be getting about 1% cosmic microwave background radiation in that static.
Wow.
And one of the patterns that we see in the cosmic microwave background is due to an effect called the Baryon acoustic oscillation, which sounds like a lot of big fancy science words, but what it really means is that in the really early universe, there were these waves due to density fluctuations in the primordial universe that behave more or less like sound waves do on Earth. And these waves, they propagated throughout the early universe while it was very hot. And the baryons, the protons and the neutrons were separate from the electrons, unlike in the modern universe where they're combined into mostly hydrogen, some helium, just normal atoms. But while they were separate, while the universe was still warm enough to keep them separate, they were coupled to the photons that would eventually make up the cosmic microwave background, and they were sort of driving these oscillations. And then at that certain point, the surface of last scattering, 380,000 years after the Big Bang, the protons and electrons combined into hydrogen, and the waves that had been traveling through that primordial universe became fixed. And while there are a lot of, there's some variation in how big these shells were that were formed by the oscillations, there is a preferred scale based on the average distance that these waves traveled. Those shells of density created by these waves propagates forward to the modern universe into a preferred distance scale between galaxies. And one of the things that we do is that we measure the average distance between these galaxies in redshift and in 2D space on the sky. And we use theoretical estimations of what the physical length scale was at that surface of last scattering. And that is our inverse distance ladder, we call it. So instead of going from the local universe out, we go from literally as far back as we can see forward to the modern universe. We can trace the sound horizon is the term for that length scale in the initial universe. And we can trace it in different galaxy types as we go from the surface of last scattering towards the modern universe. At the highest redshifts, we have what are called quasars or quasi-stellar objects, because they initially appeared to just be point sources like stars. And these are early galaxies with supermassive black holes at their centers that are accreting lots of matter. They're just gobbling up all the gas that's surrounding them, creating this very, very bright, very variable source in their center. Those quasars, because they're so bright, we can see them further than any other tracer. So we can measure the Baryon acoustic oscillation at a redshift of almost 4, which is about when the universe was roughly a fifth of the size that it was now. While the quasars are observable that far out, there aren't quite as many of them as there are of the other galaxies. So as we get closer and closer, there's other tracers that we use to measure this sound horizon. In intermediate redshifts, mostly closer than quasars, there's what's called emission line galaxies, which, while they aren't particularly bright overall, they have lots of ongoing star formation, which creates these very strong emission lines, hence the name emission line galaxies, of oxygen in different ionization states. and we can measure that very clearly. It's actually this oxygen line is a doublet, meaning that instead of just one peak like the hydrogen lines that you mentioned, we can measure two separate peaks at a very well-known separation, which means that even if we aren't getting a whole continuum spectrum or any other lines, we can tell that based on the relative strength and size of those two peaks in that doublet, that we're getting one of those galaxies at the correct redshift. And then moving even closer, there's what's called luminous red galaxies, or LRGs. And these are red and dead because they're not forming stars anymore like the ELGs, but because they have a lot of pretty stable red stars, these luminous red galaxies, even though they don't have the strong emission lines, most of them, that the emission line galaxies have, they have a feature known as the 4,000 angstrom break. And so around 4,000 angstroms, the spectrum goes from a nice flat continuum and it sort of just drops off a cliff. It just, there's a bunch of absorption lines due to these older stars, the metals in their atmosphere, and the spectrum just sort of goes from very bright to much less bright. And you can measure where that dip happens from a redshift of around 0.4, which was where the first supernova measurements of dark energy were made, out to about redshift 1, which is about half the size, the universe being half the size it was. That's basically how DESI works. We go from the cosmic microwave background. We measure quasars that are very far away, very old, emission line galaxies where lots of stars are forming strong oxygen 2 emission lines in the intermediate range. And then relatively close to Earth, there's luminous red galaxies that have the 4,000 angstrom cutoff that we can also measure. Then as we get even closer, there's what's called the Bright Galaxy Survey, which is any very nearby galaxies that we can point at and get redshifts for. These will often have features similar to LRGs or ELGs. They'll have many emission lines of various elements, various metals. Fun fact, astronomers call everything that is heavier than helium a metal.
Yeah.
So yeah, my favorite metal personally is oxygen.
Yeah, I really like to breathe.
Yeah.
I eat, sleep, breathe metal.
Mm.
I am just that cool.
Astronomy is the most metal science.
Your research with DESI is all about mapping the universe, like getting a 3D map of the universe.
Yes.
Not just where things are on the sky, but how far out they are. How does that contribute to specifically the field of dark energy? It is called the Dark Energy Survey, but
yes.
how does that tie into dark energy?
Excellent question. So the way it ties in is that what we're measuring as we measure these redshifts is we're measuring the evolution of a distance scale, that sound horizon, as we go backwards in time, I guess. You're measuring how that sound horizon goes from where it was first frozen in at the surface of last scattering, and how it expands as you go forwards in redshift and hence distance and time. And that evolution measures the expansion history of the universe, which is how we measure dark energy, just the shape of the expansion history of the universe.
Those were all of my specifically science questions, which is really good because we're hitting my threshold for maximum science of the day. Well, really, we're not. We're about halfway there, but I need to spend the other half analyzing the second half of the first season of Attack on Titan that we're rewatching. Happy quarantine, everybody. Yeah, but yeah, I gotta figure out how that ODM gear works. I'm showing Attack on Titan to my wife, so
nice.
We've gotta save about half of my science for the day just on analyzing ODM gear and how conservation of mass and energy works for the Titans.
It probably doesn't, but
hey,
then again, I haven't watched Attack on Titan.
Honestly, it's been a great 2 days. We're already halfway through season one. So, do you have any advice for people who are maybe in high school or college and are thinking of pursuing a graduate degree in astronomy or thinking of going into academia to study astronomy? And also advice for people who either don't want to or didn't study physics and astronomy, but are interested in the kinds of things you have to say. Are there any resources they should be checking out?
Let's start with people in high school or college and things that might be helpful for studying astronomy in an academic setting. First off, in high school, remember you're still a kid. Have fun. Don't like throw yourself entirely into it. It's a great way to burn out. But there are definitely some things you can focus on to start to better prepare yourself for to study science. One of them is learning programming. Honestly, you think, oh, but physics is a bunch of equations, or astronomy, you're pointing a telescope at the sky. Why do I need to learn how to program? Well, every telescope is driven by computer commands now. You're not the old 1920s astronomer like hand cranking their 75-inch refracting telescope to point at whatever stars you can see through a telescope that size. And all the data analysis is done pretty much through Python. There's some C++, but definitely learning to program is going to be at the core of pretty much all scientific research. So even if you don't know if you want to do astronomy, physics, chemistry, you're going to want to be handy with a computer.
That's actually hilarious because I asked Nora the same question, and her thing was high schoolers have fun, you're in high school, but also learn to code. Like you had almost the exact same advice, and I think that's excellent.
Well, there's one more thing that I wanted to add on sort of a personal note. I never liked writing in high school at all. I thought like early on that like, oh, in science that the writing isn't going to be as bad as in like other academic fields where like the whole thing is like writing books. You're writing papers all the time too. Like don't put off the other stuff. The other stuff is still important. Even if you're positive, like I want to study dark energy, you need to focus on the other things too. They're going to be important for both your just general intellectual development and in your day-to-day operations as a scientist.
Yeah, you're going to be reading papers, you're going to be writing papers, you're going to be editing papers, you're going to be
reviewing, presenting.
Yeah. You're going to need to make a poster, you're going to need to talk in front of people, you're going to need to answer questions on the fly. Those public speaking skills.
Public speaking.
Yeah.
First class speaking project I had in high school was in Latin. I forget the exact topic. I got like a 93 or 95 on it. He said the presentation was excellent, but you were visibly rocking and you were talking way too fast for most people to understand what you were saying. So I got a lot of excellent advice at my high school on speaking and writing. Go Firebirds, Kellenberg.
I remember getting that critique too, that I talk too fast. I would never rock. I would always be at a podium and I would clench the podium. But I would always speak too fast. I tried working on it, but now I just speak really fast, but I'm on YouTube. So you can go down to the settings and slow me down if you want. Which
25% speed and then only be a little faster than normal.
Exactly. And I'll have a lower voice. Many of you have said my voice is too shrill. If you think I talk too fast and my voice is too shrill, just, go to the YouTube setting, turn me down a little. I won't mind.
When you're in high school, you won't always have the opportunities that you do when you're at a university. And so one of the things that's especially important once you're at college is to find a group that is doing research on campus and start doing research. It's not always easy to find a group, especially one that has room for an undergraduate, and if it's, over the summer when you're not like taking classes, finding one that could actually fund you, that's very challenging. There are often resources on campus that will help with that, as well as REUs, research experiences for undergraduates, a federally run program that helps to fund undergraduate research. And there's a lot of opportunities out there, and there's nothing that prepares you for research quite like doing research. Your courses will teach you some things, learning coding will teach you some things, but getting involved in actual research is an irreplaceable experience. There's nothing quite like it. It'll certainly let you know if that's what you want to do, and if it is what you want to do, it'll prepare you for the next stages.
You should definitely do research, especially if you're not sure. I know that I did research, and my first research experience made me realize that I wanted nothing more than to go to grad school. My second research experience made me realize grad school, not really for me. So try to get as many research experiences as you can, because not only will it help you get into grad school if that's what you choose, but I and many people I know did research thinking that they wanted to go to grad school and are now not in grad school because they realized it wasn't for them. And it's much better to figure that out in college than halfway through a PhD.
Oh yeah. Yeah, you don't want to invest all that time to find out that it wasn't for you. That's miserable.
Yeah.
You still learn things from doing research, even if all it is that you don't like doing research, which is a very important thing.
Oh yeah, like do research even if you're not sure. Just always do research. Research is great.
Yep.
She says after talking about how she hates doing research. Yep. No, I enjoyed all of my research experiences. I just realized a PhD was not the route I wanted to go. That was really good advice for high school and early college students. For people who maybe discovered that research isn't for them, or who don't like math, or just never studied any STEM fields or studied chemistry, squishy physicists are welcome here. For people who didn't study astronomy but would still like to maybe keep track of the dark energy search and the dark and DESI, do you have any resources that you'd like to plug? Is there any outreach that your university does? I will happily put the links down below.
One of the great things about astronomy is that it's one of the things that you can do as an amateur, and amateur astronomers they've always had a place in the astronomy community. Even as recently as 2014, one of the most, important discoveries of an individual supernova was made by an amateur astronomer. I think it was in Ireland. Supernova 2014J was the nearest Type 1a supernova in many years. One of the only that supernovae that close that had gone off in the era of like modern digital telescopes. In the early days, they used photometric plates. Now they use sort of the same digital cameras that are in your phone or your DSLR. An amateur astronomer was the one who first discovered that it was there, and then every telescope on the planet pretty much just started pointing at it for a while. So there's a lot of space for amateur astronomers in that sense. And there are, for people who live in cities and can't see anything brighter than the Big Dipper, there's also citizen science projects. Yes, all of us. Citizen science, which is scientists have a project that's like, we need a lot of bodies to throw at this, more than we have on our collaboration. We just want people, like actual human brains, not algorithms, to look at these images usually and tell us what they see. And it started out, at least in astronomy, with this project called Galaxy Zoo, where people would look at Sloan Digital Sky Survey images and classify galaxies, whether they were elliptical, so sort of like oval shaped and solid, or whether they were more spiral, like the Milky Way with visible spiral arms. And they could also flag objects, whether they were, if they were like particularly interesting, whether they were like unique color or shape, whether it looked like they were merging, if you could sort of see two galaxies touching each other in the image. they actually, using data from this galaxy zoo, discovered a new type of star-forming galaxy called a green pea. And there were actually several papers published on this new type of galaxy using data from a whole group of people and their only requirement was having an internet.
Yeah,
no formal training. There was like a little tutorial. I did it back in high school, some classification for it. And it's actually erupted this huge project, not just in astronomy anymore. It's called, because the original was Galaxy Zoo, they call it the Zooniverse.
Mm-hmm.
Get it? And there's tons of projects. There's still the original like galaxy classification projects. There's a project on looking at, I think it's supernova light curves from what I think is the coolest named survey, Assassin. And there's
astronomers should not be allowed to name things.
Counterpoint, only astronomers should be allowed to name things. But yeah, there's a lot of fantastic astronomy acronyms that exist. Assassin is the all-sky automated survey for supernovae. Assassin.
I should do a whole video just on astronomers naming things, because there are lists out there of the crazy ones. There was like a Holy Cow project. There
Holy
was
Cow,
the Minerva, which I think is cheating.
I mean, Holy Cow is cheating too, because the O is a 0.
Yeah, because it was
every good like acronym in physics and astronomy cheats.
Oh yeah.
There is some cheating. Like there are a lot of ones that are good that don't cheat, but the great ones all cheat.
Oh yeah.
It's just like, home run hitters in the 1990s.
Yeah.
My personal favorite, and one that I was involved with the sort of start of bringing it to Chicago, at least, is Astronomy on Tap, which has chapters in many different cities around the country and around the world, where pretty much the format is get astronomers into a bar, tell people that astronomers are going to be at that bar, and talk about science. There are a bunch of different ways that happens. Usually they'll have a featured speaker who will talk about their own research. There will be like question and answer sessions. Usually there will be some sort of fun game or activity. I would write the trivia questions for the Chicago area Astronomy on Tap that we would run at the University of Chicago. We also shared a sort of organizational structure with Northwestern, which I know you like quite a lot, Northwestern.
School, work there now.
Yeah.
It's fine. It's a cult. I'm never leaving.
Oh, okay. But yeah, we had a great time there, met a lot of interesting people. I doubt that it's currently running, but once people are, back, once things are back to normal, then there will definitely be opportunities for that in most cities, but especially in Chicago and New York, where I'm originally from. There are excellent planetariums that have shows that will teach you about pretty much whatever topic you want, at least at Adler on a Adler in Chicago or Hayden in New York. On a rotating basis, they'll rotate through every hot topic in astronomy research. I saw a presentation on the search for Planet 9, a presentation on dark energy at Adler. And at Adler in particular, there's it's been so long I've actually forgotten the name. The SVL, the Space Visualization Lab. Thank you. And they would have
both worked at the Adler.
Really impossible to do.
If the Adler ever opens up again, please hire me back. I miss you so much. I started a YouTube channel.
But yeah, they would have University of Chicago, Northwestern, and other local physicists and astronomers come in. And in addition to talking about their own research, they have tons of amazing visualizations developed by scientists in the area and around the country, possibly around the world. I don't remember the list, but there were definitely tens to hundreds of astronomers involved in developing these visualizations that show everything from one of the possible mechanisms for supernova formation to all the asteroids that are currently whizzing by Earth, like as we're talking, asteroids getting within a moon's orbit of the Earth. And just we know because of how well we measure them that they're never going to hit us. But when you show it to people, they're like, that's there, and yep, it's right there, and we know it's never going to hit us.
Yeah, and I think what James is suggesting, just to summarize, because that's my function, is that what you should do is wherever you are, maybe look into your local college, university, any local museums, see if they have astronomy on tap, see if they have any of these events, show up, get blackout drunk, ask them about the Fermi paradox, and tell them James Lasker sent you.
Exactly that. Other than maybe don't get blackout unless you're recording. You do want to hear the response and remember it.
Get brown out, bring a voice recorder. Say, I want to ask about the Fermi paradox. Dr. Lasker sent me, and then show them a picture of James that you pulled from this video.
Oh, yeah.
And tell them,
and yeah.
And tell them that you've used him and his work to disprove Einstein.
Absolutely. That's the goal.
And then you can bring up Pluto.
And then bring up Pluto, which is, totally a planet.
Oh, did you say Pluto is a planet?
I think Pluto is a planet in my heart. I understand why it's no longer a planet scientifically, but
no, Pluto is a planet on this channel. This is a Pluto safe space. we acknowledge it's a dwarf planet, but we think dwarf planets are planets too. My writer Eris, back when we were working at the planetarium, asked a child, like a 5-year-old, whether Pluto was a planet, and the child said no. So Eris asked, well, why isn't Pluto a planet? And the child said, it's too small. And Eris looked at her dead in the eye and said, does that mean you're not a person because you're too small? The child's brain broke and the parents died laughing. It was a good time had by all.
I feel bad for whoever had to clean up the brain matter.
It's fine. Various child goop is part of the day-to-day routine.
Yeah. Familiar, but still disturbing when you see it the first time.
Yeah. Anyway, so can we at Bad Astra count on you to be Team Pluto as a planet?
Yeah, of course. Always.
It's very important. It's very important. So, by the way, the fist fight with Nora Bailey is scheduled for, you and Eris will be fighting Nora Bailey, although she is going to be bringing words. So that is her weapon of choice. Choose your own weapon. We're building sharks and jets style teams.
So you're saying I should have like a musical number?
Oh, definitely. Like if she's bringing words, you need to step up your game. You need to bring a grand piano because keyboards, it's too thin. No. Come on, keyboards are too synthetic. You gotta, and like maybe you could bring a guitar, but really, if you're going,
what about a keytar for the flair?
Yeah, bring a keytar for some flair. Because I really think that if all she's coming at you with is words and you bring out a musical number with Eris, there's no way she stands a chance.
Oh, no way.
No way. So, James, I have a question for you. Since you are a physicist and you should be able to answer this, should my puppy, who is perfect in every way, she was barking throughout this interview, I maintain that she is perfect in every way, we'll edit it in post, I believe that she should deserve a Nobel Prize in physics. What are your thoughts?
Well,
now, before you say anything, I have 2 pieces of evidence to present. Hold on. Piece number 1. She is the most adorable little puppy. I mean, look at her. Look at her. She was just napping and now she's here. Hello. Doesn't this puppy deserve a physics Nobel Prize?
It's very hard to say no to that face.
Yeah. My second piece of evidence is that before you make a decision on whether this puppy gets a Nobel Prize in physics, oh my God, she yawned. This is Cecilia Payne. My puppy's name, yes, is Cecilia Payne. And as you know, Cecilia Payne is the one who used Annie Jump Cannon's spectroscopy catalog to determine that stars and the universe overall was made up of hydrogen mainly and a little bit of helium. So, do you think that for the discovery of the entire makeup of the universe and the most adorable yawn ever captured on camera, that Cecilia Payne, my golden doodle, should win a physics Nobel Prize?
Mm. Let's see. On the one hand, that's, an incredibly amazing discovery. And also on that one hand, that is the cutest dog I've ever seen, and that dog is incredibly adorable. On the other hand, I think one of the requirements for a Nobel Prize might be being human. I don't know if we've ever awarded it to a non-human.
See, I feel like that's discrimination.
It is.
And especially this anti-dog discrimination, especially since Cece is a girl dog. And I think that because she was a girl puppy and is only 4 months old and therefore was only a postdoc, or was she a graduate
student?
Sorry.
Yes, 4 months. If you're not in grad school by 4 months old, just
give up.
Yeah.
But since my puppy is only 4 months old and is only in grad school, her discovery about hydrogen was contradicted by a professor, and she had to go back on it, which is why she has not yet won a Nobel Prize. And I think the fact that she's a dog, not a human, is just you trying to avoid the question.
Well, you got me. So Cecilia Payne, she was. There were 3 separate dimensions in which she was conspired against. First off, there was, not a lot of respect for women in the field then. Even in the 70s, there was Jocelyn Bell, who, for similar reasons, both being a younger student and being a woman, was sort of drowned out by her advisor and not given the Nobel Prize for the discovery of pulsars.
Yeah, Jocelyn Bell's even worse because the Nobel Prize was awarded to a professor who took credit for her work.
That's true. That's even worse. And that brings me to the second point in which Cecilia Payne was screwed up, was that they didn't really like giving physics Nobel Prizes for astronomy back in the early days. The first even tangentially astronomy prize was given in the 30s for cosmic rays. And that was mainly for the discovery of particle jets. So it was a particle physics prize to first order. Then the first one was for the radio astronomy for I think it was the pulsars in the 70s. That was really a pure astronomy prize. And then also, as you mentioned, that she was a graduate student. People don't tend to, for truly groundbreaking discoveries, they tend to give the credit to the faculty member, because in some cases, but not all or even most, they are the ones who come up with the initial idea that sparks the experiment.
And I think it's getting better.
It is getting better. The Nobel Prize for the Type 1a supernova discovery, that half of it for the team at the Harvard CFA. It was given to, I think when the prize was awarded, I think they were professors, but when the discovery was made, one of them was a graduate student and one of them was a postdoc. Adam Rees, one of the 2 people from the Harvard group to receive the Nobel Prize for discovering the accelerating expansion of the universe with Type 1a supernovae. Part of his thesis was standardizing the luminosity of Type 1a supernovae, which led to the Nobel-winning discovery.
I think it's really good that we're making that progress, because I feel like it's not just Jocelyn Bell and Cecilia Payne. There is a long, long list. It's very common to have lists of women who should have won Nobels. I'll probably do a video on that, but there are loads of people who should have won Nobel Prizes who didn't because the Nobel Prize committee is not infallible for some crazy reason.
What?
You mean an organization made up of people might be inherently political?
I never would have guessed.
Now that you have come out in favor of Pluto being a planet,
Of course.
but against my dog having a Nobel Prize on some
it was a tough decision.
speciesist grounds. She's 4 months old and she's perfect. How could you deny her?
She is pretty much the perfect puppy.
Thank you so much to Dr. James Lasker for doing this interview. Thanks to everyone who stayed to the end. If you had a good time here, please feel free to check out other videos, give this video a like, comment any questions you have. Feel free to subscribe. Please subscribe. I would love it if you subscribed.
I subscribe.
Yeah. Be like Dr. Lasker and subscribe. Remember to always keep an open mind and get excited about science. Astra out.
Ad Astra, to the stars, to the stars.
Thank you so much for joining us here on Bad Astra. If you enjoyed watching, please like this video, leave a comment telling us what topic you'd like to see next month, and share it with everyone you know. Be sure to also subscribe and ring the notification bell so you never miss a new episode. And if you can't get enough of me, Eris, and Science Tommy, join our Patreon, where we post behind-the-scenes deep dives and other fun content. A special thank you to all of our Patreon supporters who make these videos